Much of history is highly contingent. Things could easily have developed very differently. If the Earth had not been struck by an asteroid 65 million years ago, perhaps the dinosaurs would have developed intelligence instead of mammals. It seems that in principle, a dinosaur civilization could have arisen given the right evolutionary developments. Hitler could have won the war. More prosaically, while I had a banana for breakfast this morning, I could have had cereal instead. An interesting debate in the philosophy of science concerns the degree to which the results of science are contingent. Could science have developed differently? On some interpretations, this question is fairly trivial. There are some obvious ways in which science is contingent. If there had been a nuclear holocaust 50 years ago, then science would presumably have ended then. Or if there had been an oppressive state that forced scientists to adopt particular views, as happened in the Soviet Union with Lysenkoism in biology, then science would have taken a different path. Clearly, then, the development of science is closely dependent on the general social conditions. But there is, I think, a more interesting question here. Assuming that scientists were free to pursue their research, that science was still successful, is still basically the institution we have in the actual world, could the scientific theories that were developed have been substantially different? Could a successful physics have developed without postulating quarks, without incorporating anything like the Standard Model? Ian Hacking, in his article, How Inevitable Are the Results of Science, phrases the problem as follows. He says, if we were to be successful in science, such as cosmology or cell biology, with something like our current interests, would we have to arrive at or pass through something roughly equivalent to our present cosmology or cell biology? Now, yes, this question is imprecise, but you should be able to get the general point. And broadly speaking, there are two positions here, inevitabilism and contingentism. Now, according to inevitabilism, the results of science are inevitable, and in the sense that, to quote Hacking, any other properly resourced and rigorously conducted investigation of the same subject matter would have contained or implied the same result. Emiliano Trizio, in his article How Many Sciences for One World, draws a useful comparison to geographical discoveries. We might not have chosen to try to sail around the world, but assuming that you have a working ship, and assuming that you set to sail as far west as possible, so that is, you sail continuously in the direction of the sunset, then hitting the American continent is inevitable. Anybody who makes the same journey from European shores will arrive basically at the same place. You'll arrive at the American continent. The inevitabilist suggests that similarly, any scientific practice that's properly funded and that has academic freedom will inevitably hit upon largely the same theories as ours. Contingentism denies this. The contingentist says, if you replay the tape of the last 300 years, well, we could have developed a science just as successful as our current one, but it would have nothing like quarks and electrons, it would have nothing like Maxwell's equations, or general relativity, or Mendelian genetics, or the central dogma of molecular biology, or the second law of thermodynamics, and so on. Now, instead of thinking in terms of replaying history, we can also frame the inevitabilist contingentist debate in terms of a race of intelligent, technologically advanced aliens. If there are such beings, must they have developed pretty much the same scientific theories as us? The inevitabilist says yes, the contingentist says no. Obviously, these views are not strict camps, they're different ends of a spectrum. You can hold inevitabilism or contingentism to stronger or weaker degrees, but broadly speaking, those are the two possible views here. So, I think it's fair to say that the common sense view is inevitabilism, and certainly I think if you ask scientists themselves, they tend to be inevitabilists. Maybe there's a bit more contingentism in the sociology of science and history of science and so on, but inevitabilism does seem to be the sort of common sense position here. So we're going to start this video in this video by looking at some of the objections to inevitabilism. And then in the next video, I'll look at the objections to contingentism. Okay, so one objection to inevitabilism from Ian James Kidd in his article Inevitability, Contingency and Epistemic Humility is that in order to state her thesis in an even remotely plausible way, the inevitabilist will have to build in all sorts of qualifications, and she'll have to build in so many qualifications that for all practical purposes, inevitabilism just collapses into contingentism. But basically, right, the inevitabilist doesn't simply say it is inevitable that physicists postulate quarks. Instead, she says something like, it is inevitable that physicists postulate quarks just as long as ... where the ... contains various conditions. And these conditions might include, for instance, the inevitabilist is going to assume the existence of certain institutional structures and disciplinary relations. She's going to assume the existence of certain scientific concepts and methods and instruments. She assumes that we ask certain questions about the world, and so on. If we had asked different questions about the world, we may never have postulated quarks. If we had not developed the same instruments, we may never have postulated quarks, and so on. So there's a huge list of various qualifications that have to be built into the statement of inevitabilism, and all of these are subject to contingencies, because the questions that we ask about the world are contingent. The kinds of scientific instruments we have are clearly contingent. It might have been the case that we just decided not to fund particle accelerators. Maybe we might have decided to spend a lot more money on other sciences, or we might have allocated the money to things that aren't science. Or physicists might just have decided to pursue different types of experiments that didn't involve the kinds of particle accelerators we have today, and so on. So any result of science relies on a huge range of factors, social, financial, intellectual, material, all sorts of different factors, many of which are clearly contingent. So Kidd argues, once we build in the range of conditions required to make inevitabilism plausible, the claim just collapses into contingentism. Science is contingent in all the ways that matter, basically. Physicists didn't have to postulate quarks. It could have happened differently. Both the inevitabilist and the contingentist agree on this. Now, I do think it's clear that inevitabilism can only be a conditional claim of the form if X, then Y. So, if physics is properly funded and physicists have academic freedom, then physicists will develop theories that postulate quarks. Kidd argues that the antecedent of this has to include a huge range of different factors, all of which are contingent. And so inevitabilism is really just collapses into contingentism. So how might the inevitabilist respond? Well, I think it's very questionable whether the statement of inevitabilism does in fact need to include all these conditions. I would say that actually we don't need to say, provided physicists had asked the same questions and had developed the same instruments and so on. Because we can hold that asking different questions and using different instruments would still have led physicists to quarks. It would still have led them to the same results. And in fact, just as a historical matter, we know that different questions and different instruments can lead to the same results. So regarding different questions, scientists have been led to propose similar theories despite asking different questions about the world. These are cases of independent discoveries of the same theory. Charles Darwin and Alfred Russel Wallace independently conceived of evolution by natural selection. Very broadly speaking, of course, they did ask the same question, in that they were both asking the question of, well, what is the origin of species? But when you look a bit more closely at their research, they were interested in different things. They engaged with different parts of the biological world. So it's not really clear that that they were asking the same questions. There were a lot of differences between them. Similarly, we might also note that there are serendipitous discoveries. There are discoveries that occur just by accident, not as a result of any particular questions. A classic example is the case of the discovery of pulsars by Jocelyn Bell and Anthony Hewish. Bell and Hewish were working with a radio telescope searching for quasars, and there are specific types of radio emissions that indicate quasars. Just by chance, Bell detected a series of radio pulses spaced perfectly evenly apart, about 1.3 seconds apart. Now, this discovery was completely unrelated to quasars. These pulses were eventually identified with rotating neutron stars. This illustrates that it doesn't necessarily matter what questions you ask. Some discoveries you just stumble upon simply by pointing instruments in the right directions. Similarly, we know that different instruments can detect the same phenomena. I'll consider the different ways of detecting X-rays in astronomy. A number of different instruments can be used to detect X-ray flux from sources beyond the Earth. One instrument is known as the proportional counter. I'm simplifying it somewhat here, but this is enough detail for our purposes. So the detector is filled with a gas composed of a mixture of a noble gas and methane, so argon and methane, for example. There is a window that is thin enough to transmit X-rays. When an X-ray photon enters the detector, it is absorbed by an argon atom, and the argon atom emits an electron. Now, the detector also contains an anode, which has an electric field. The electron produced from the ionisation of the argon atom is attracted to the anode, and on its way there it collides with other atoms, causing further ionisations, which itself produces even more electrons and more ionisations as they travel toward the anode. So you get this kind of avalanche of electrons close to the anode. So suppose this is the path of the X-ray. It ionises an atom, the electron travels to the anode, where it then causes further ionisations. Due to this avalanche of electrons close to the anode, you get a charge which is detected. Now, a bit of a problem here for the proportional counter is that it will also detect cosmic rays. Cosmic rays will pass through the walls of the detector. So we use a second counter known as a guard counter, which is placed close to the X-ray detector, and any cosmic X-rays which hit the X-ray detector will probably also hit the guard counter, so any event that is detected on both detectors simultaneously is treated as a cosmic ray and is discounted. But that's basically how you detect X-rays with a proportional counter. Another instrument is the scintillation counter. Again, this is simplified, but basically this consists of crystals of sodium iodide or cesium iodide. An X-ray photon is absorbed by an atom of the crystal, and then some of the energy of this photon immediately reappears as a flash of light or a scintillation, which is detected by a photomultiplier tube. The photomultiplier converts the flash to an electric signal. On this instrument, the guard counter is a second scintillating material sensitive to cosmic rays, so scintillations that occur simultaneously in both materials are discounted. So we have here two instruments that operate on very different principles, and furthermore they're often used in different ways. The first X-ray detectors were attached to high-altitude balloons and simple rockets. Now we use sophisticated satellites. But despite these differences, we acquire the same, or at least very similar counts from different instruments. If you point both the proportional counter and the scintillation counter at an X-ray source, say Cygnus X3, they will both give positive signals. Prima facie, what we have here are different instruments giving the same or at least very similar results. And there are many other instruments that can be used to detect X-rays. So it seems at least plausible that scientists would have detected X-rays and astronomers would have discovered X-ray sources throughout the cosmos, even if they didn't have the instruments that we do. These examples should illustrate that the inevitabilist can stick with the broad formulation of inevitabilism. provided that science is properly funded, provided there is academic freedom, allowing scientists to explore different ideas. So provided, in other words, that we have a free, sophisticated society analogous to our own society, the results of science are inevitable. This claim, of course, may not be true, but it doesn't collapse into contingentism, which is the criticism in question here. Ian James Kidd claims that inevitabilism collapses into contingentism. I'm not really sure that's the case. I think we can state inevitabilism, at least a plausible inevitabilism, without collapsing into contingentism. However, the inevitabilist isn't quite out of the woods yet. Ian Hacking has suggested, in perhaps a somewhat different way, that inevitabilism may be trivial. To make this objection, Ian Hacking considers investigations of the velocity of light. The inevitabilist claims that it is inevitable that scientists would have found a speed of light about 186,000 miles per second in a vacuum. It's a fact of nature that light travels at about 186,000 miles per second in a vacuum, and any serious, careful investigation of nature would reveal this fact. But the problem is that this claim is just empirically false. The first determination of the speed of light was made by Ole Rømer by timing the eclipses of Jupiter's moon Io. He came up with a figure of 140,000 miles per second. So the currently accepted result is not inevitable. I mean, that's just historically clear because people have come up with different results. So in order to secure inevitabilism, we need to add something along the lines of, well, if Rømer had used sufficiently precise equipment, and if he had used it with sufficient skill without making any mistakes, then he would have arrived at the figure of 186,000 miles per second. Now, we need to say, if Rømer had used the right instruments and had made no mistakes, he would have arrived at 186,000 miles per second. And the question then is, what counts as the right instruments? Well, it looks like from our point of view, the right instruments are just those instruments that deliver the results that we accept. I mean, if somebody uses an instrument and gets 140,000 miles per second, then it can't be, something must be going wrong from our point of view. We would say that's not one of the right instruments. Similarly, what counts as not making mistakes? Well, using the instruments in such a way that you get the results that we accept. So this seems kind of trivial, because we're no longer dealing with an alternative science. We are now imagining a science that proceeds in all the ways that matter as ours does. And this is because we can only judge whether something is a good instrument or whether the scientist has made a mistake by the results that we accept in our current science. So I think Hacking is sort of trying to pose a dilemma. He's saying, look, when we state inevitabilism, we can either include a normative condition where we say that the results of science are inevitable provided that no mistakes are made, right? Or we don't include this normative condition that rules out mistakes. The problem is that if we include the normative condition, then inevitabilism is trivial, but if we don't include it, it's just obviously false. It's straightforwardly falsified by cases like Ole Rømer. So perhaps that is a problem. Right, another objection to inevitabilism is it seems there are cases where theories are accepted or rejected on the basis of what we might call crucial pieces of evidence. A good example of this, pointed out by Howard Sankey, can be found in the development of plate tectonics. We know today that continents move very slowly around the Earth. This was first proposed by Alfred Wegener in the early 1900s, and a great deal of evidence was appealed to by defenders of this theory. So this included evidence based on patterns of continental shelves, which seemed to suggest that they once fitted neatly together, as shown here. So this is the proposed Earth of the past, and then you can see these continents gradually drift apart. But you can see that, for example, Africa and South America seem to sort of fit together in this. They sort of have this jigsaw fit. Furthermore, there were similarities in geological features across different continents, such as the Canadian Appalachians seemed continuous with the Caledonian Mountains of Scandinavia. So not only do the continents fit together, but we find that geological features match up as well. Wegener compared it to putting together bits of paper that have been torn up and finding that the words on one part form a coherent sentence with the words on the other. Now, this would be very strong evidence that the bits of paper were originally one. Proponents of drift also appealed to paleoclimatological data. For example, there is strong evidence that during the later Carboniferous period, extensive glaciation occurred in South America, South Africa, India, Australia and New Zealand, and that's shown here on this top map. In black are the regions of glaciation. At the same time, Europe and North America enjoyed tropical climates, so it couldn't have been a worldwide glaciation. Wegener explained this by suggesting that these areas of glaciation were once connected at the South Pole. Now, there were various other bits of evidence as well, none of which was convincing to the scientific community. Numerous objections to drift were raised. Wegener's theory languished for several decades. Ultimately, the recognition that the continents moved around the Earth occurred thanks to studies of the ocean floor. Some minerals are magnetic. When they are formed from lava flows, they align with the Earth's magnetic field in the same way as your compass needle. When we examine the sea floor near mid-ocean ridges, we find these strips of magnetic rock with alternating polarity. And we can explain this by assuming that the sea floor literally spread out from the ridge. So here it is in the past, moving towards the present, and you see that the sea floor is spreading out. So as new ocean floor is created, the magnetic polarization of the Earth is imprinted onto the rocks. But what happens is that the Earth's poles undergo magnetic reversals, and there's a lot of evidence that this occurs every few million years or so, I think. So what you get is, as the seafloor spreads out, when the Earth's poles reverse, the rocks end up with opposite polarization, and you end up with this sort of pattern of alternating polarity. It's very difficult to explain this pattern without postulating the spreading of the sea floor. And this is what converted the scientific community to accepting that the continents moved around the Earth. But what's important is that this evidence was hard to come by. I mean, in general, gathering evidence requires a great deal of effort. It seems like this effort could have gone differently. We might not have uncovered these patterns of alternating magnetism. In that case, continental drift, it seems, need not have been accepted. None of the other evidence cited by the proponents of drift was considered sufficient. So, I mean, the basic form of the argument here is that certain theories are accepted on the basis of single pieces of evidence, but gathering that evidence is highly contingent. Hence, the acceptance of the theory must be highly contingent as well. Now, I think there are a couple of obvious ways the inevitabilist might respond to this argument. First of all, we can question, well, is it really true that there are such single crucial pieces of evidence? I mean, as a historical fact, the discovery of seafloor magnetism converted the scientific community in a way that none of the other evidence did. But then how can we rule out there being other kinds of evidence that would have had the same effect? Indeed, notice that if the contingentist says that acceptance of a theory requires uncovering some piece of evidence X, that kind of looks a lot like inevitabilism. So that's perhaps a concession that's a claim the contingentist might not want to make, because you're saying that acceptance of a theory is, depends entirely on one piece of evidence, which sort of seems in tension with the basic idea of contingentism, that science is open and can develop in many different ways. But another question here is whether the discovery of seafloor magnetism really was dependent on contingent factors. Now, I admit that I'm not so familiar with the historical details of this particular discovery, but it seems to me like magnetic patterns on the sea floor is the kind of thing that we would have run into sooner or later anyway. We need to explore the oceans for various reasons, not just scientific reasons, but also that there are military and technological projects that involve the ocean. So, we need to study the ocean floor. So it looks like we would have run into this magnetism anyway. I mean, my point is, if you want to make this appeal to crucial evidence, you need to establish two things. First, you need to show that there is some piece of evidence X that plays a crucial role in the acceptance of a theory, so that without X, the scientific community would not have accepted the theory. Second, you need to show that the discovery of X is highly dependent on contingent factors. It's not something easily discovered. So if you replay the tape of the last 100 years, we would be unlikely to discover X in that replay. I don't think that seafloor magnetism meets these requirements, and I think it would be very difficult to identify cases that do meet these requirements. So I'm not so sure about this objection to inevitabilism. A final argument against inevitabilism appeals to the role of values in science. I've discussed this recently in the video on incommensurability, so maybe go and check that out if you haven't already. Philosophers of science sometimes talk about methodological incommensurability, which is the claim that different scientific traditions have different values or different standards of evaluation. There are no independent values or standards by which we can judge competing theories. Crucially for our purposes here, arguably we're not rationally compelled to adopt one particular set of values or standards. And so this means that scientific theories are contingent. Scientists could have adopted different values, and if they had done so, they would have accepted different theories. The example I gave in the previous video on incommensurability was the debate between the Newtonian and Cartesian theories of gravity. The crucial point is that the Newtonian theory gave more accurate predictions than the Cartesian theory. However, the Newtonian theory treated gravity as involving action at a distance, which seemed very spooky and mysterious to 17th century scientists who held that science should provide mechanistic explanations that always clearly link causes to effects in a mechanistic manner. The Cartesian theory gave a mechanistic explanation of gravity in terms of forces exerted by vortices of matter. So we have these two virtues, one of predictive accuracy, the other of mechanistic explanation. The Newtonian theory did better on the first, the Cartesian theory did better on the second. Everybody recognised it was a serious problem for Newton's theory that no mechanistic explanation was offered. What's interesting is that when the Newtonian theory finally triumphed, instead of trying to resolve the problem and offer an explanation, scientists simply dropped the requirement that scientific theories provide mechanistic explanations. So this illustrates how there are different values of, there are different ways of judging theories, different standards we can use, and these values can change over time. Now it seems that in principle, scientists didn't have to drop the methodological requirement for mechanistic explanation. They could have continued considering Newton's lack of mechanistic explanation to be a serious problem for his theory, and perhaps science would have developed differently in that case. And notice, of course, that Newton's theory exhibits some of the most striking predictive accuracy in the history of science. In other fields which are capable of less predictive accuracy, like biology, the dependence on other values is even stronger. So, what can the inevitabilists say about this? Well, I think the primary response to this argument is going to be that, yes, scientists can have different values, but they still share many values. And values can differ only within very strict limits. So this strongly constrains the field of acceptable theories. Theories need to exhibit accurate predictions. They need to be consistent both internally and with other accepted theories. They need to be useful in terms of promoting further research and so on. These are values that we all basically agree on. In particular, we all agree that predictive accuracy is probably the most important. Scientific theories need to issue correct predictions. Newton's triumph was inevitable in that respect, since his theory clearly provided more accurate predictions than the competitors. What we tend to find is that we appeal to other values like theoretical simplicity, when it isn't clear which theory has the most is the most empirically accurate. The best case of this is perhaps quantum mechanics. There are various different interpretations of quantum mechanics, like the Copenhagen interpretation, the many worlds interpretation. As far as I understand it, these different interpretations are empirically equivalent. They make the same predictions, at least given what present technology allows us to test. Perhaps the debate between those is decided in terms of other values. Perhaps then the Copenhagen interpretation, for example, wasn't inevitable. But what was inevitable, according to the Inevitabilist, was the theory that underlies these interpretations. Those were some arguments against inevitabilism. In the next video, I'll examine some of the arguments against contingentism. But that's all for now. Thanks for watching.